So, hi everyone. Thanks for coming to our February general meeting of the NHERI Graduate Student Council. We are really excited to have Dr. Aikaterini Katerina Kyprioti. Dr. Kyprioti received her bachelor's degree in civil engineering with a minor in civil infrastructure from Aristotle University of Thessaloniki in Greece in 2014. And then she continued her studies earning a master's degree in earthquake engineering in 2016. Afterwards, she then moved to the US, where she completed her PhD in civil engineering and a master's in applied mathematics and statistics from the University of Notre Dame in 2022. So she's recently graduated. And currently, Dr. Kyprioti is an assistant professor at the School of Civil Engineering at the University of Oklahoma, where her research focuses on integrating computational statistics into civil engineering applications, particularly in natural hazard risk mitigation. And she's collaborated with key agencies such as NOAA, FEMA, USACE on storm surge, coastal hazard estimation using surrogate modeling techniques to improve real-time forecasting and regional planning efforts. We are extremely excited to have her. Thank you for being here, Dr. Kyprioti.
Absolutely. Thank you for the invite. And I would like to stress out, being a new graduate from the Summer Institute at NHERI, I joined last summer. It's a very useful and very eye-opening experience. So for those that would like to participate, I highly recommend that. I'm so excited to be presenting in front of graduate students since it's not been long since I was one. So definitely that brings back memories. And I'll talk about my research that has been so far in natural hazard quantification, and a bunch of it actually is related to my graduate work. I feel you need to allow me to share my screen, because I'm the one that has the slides right now. So
you should always be able to share.
I think you should be able to.
Yes, I am now. I couldn't go past your presentation. That's why I guess. Makes. Okay, let's see if you're looking at the right screen. Can you see the presentation or the? Okay, great. Awesome.
Yes.
I have two screens in front of me, so I want to make sure that you're looking at the correct one. Okay, so what I'm going to be discussing today is how we can use surrogate models, so data-driven models, in storm surge hazard estimation. And I'm going to walk you briefly through a project that I was involved in, and I've been also working now to extend. And I will start. So here's the outline of the presentation. I'll try to keep it short and sweet, but I would like also to inspire some questions, or even you thinking about how you can use surrogate modeling in your applications, or how you can use data in data-driven methods when necessary. So the motivation, I mean, talking to a group that's interested in natural hazards shouldn't be hard to point out why natural hazards have been a huge stressor in our infrastructure, in our everyday lives, in everything that we look at right now. So just to give you an idea across the world, the first thing that we can observe is a very, very strong change in urbanization patterns. So we can see that more and more people are pretty much concentrating uncontrollably in certain regions. And in some cases, these regions might be very, very close to the water. So if we look at coastlines, we can see that many people tend to move towards that direction. So we have a very, very strong exposure that we're looking at. And just to give you an idea, when we're looking specifically at hurricanes, there are the fundamental, the foundational hurricanes that we've ever experienced, like Katrina and Superstorm Sandy. But even if you look at 2020 across the United States, we had a record season where we had a bunch of different, actually we had run out of letters at that point naming those hurricanes. So we ended up with a bunch of, guess what, Greek letters that they were trying to name the hurricanes after. And as you can see, the aftermath is very, very huge. You can see at your right screen, at the right side of your screen, that we're looking at billions of dollars in damages, and in some cases, we might be looking also at fatalities, which are the things that as engineers we're primarily concerned with. But that's not only something that's indigenous to the United States. These events are happening all across the globe, and climate change is one of the reasons that we see them intensifying, along with a bunch of other weather patterns that they bring extreme events in our everyday life. But even not without the climate change, we have a bunch of other stressors that are related to natural hazards that have caused and keep causing and will be causing disruptions to our environment and our everyday lives, our economy, you name it. There is a very, very wide net that they're casting. And what we are called to do from our side is to take proactive measures, so be able to somehow predict how these things will occur, what will be the magnitude, and what will be the level that they will affect our everyday life. So on top of that, if an event is evolving, like a wildfire or something else, like a hurricane approaching, we should be also able to offer well-informed emergency response management. So using tools that we have available, we want to work simultaneously in two fronts. One says, what can we do as the natural hazard, as the disaster evolves? And then what can we do? And this is the short-term view. And what can we do in the long term so we can plan ahead and inform our decision-making about the things that will happen in the near future based on the trends and the things that we do. So exposure to natural hazards is directly related to uncertainty and therefore risk. So, and just to give you an idea of that uncertainty that we are discussing in a broader context, you can have uncertainty when it comes to hurricanes approaching. These are different advisories for Hurricane Eta that are with 4 days apart, and you can see how the affected region or the cone of uncertainty that we have switches entirely the state that is about to hit. So there is that inherent uncertainty to the phenomenon itself. There is also uncertainty that might be related to much more long-term and non-stationary phenomena like the sea level rise. And you can see that we have different models that they're predicting different evolutions for that. But if you also want to focus in other events like earthquake excitations that are stressing our buildings, you can have uncertainties that are related to the earthquake excitation itself, but also to the structure that you're looking at with the parameters that it has and the damage that you will experience at the back end when you're looking at such an interaction. So bottom line, we have complexity in the natural hazards that we're dealing with, and each natural hazard is bringing a different complexity onto the table. And on top of that, we have interdependencies that are related with our infrastructure systems, and not only with them, but also with our society, with our political and economic sceneries on top of that. So, but what we have as graduate students or researchers overall is that due to the technological advancements that we're looking at, we have high fidelity, what we call high fidelity models that can faithfully and accurately simulate such processes and map such interconnections at a broader sense. So we have networks, we have a bunch of different tools that we can use so we can replicate or even mimic what actually is happening in the real life. But what these models, what we call high fidelity models, the very, very detailed ones you might think of in your discipline, each one of you separately, they do come with a high computational cost. So they come with a strong requirement in the memory you need to allocate for them. In some cases, also the time that it takes to just run a single run out of them. And also they require your knowledge, our knowledge when it comes to how to execute and run those models. So this is something that definitely cannot be performed in a wider range from people that just will hit a button and have that simulation of a potential event simulated. So just to give you a broader picture of the vulnerability assessment framework. So what we're dealing with is pretty much, this is the flowchart of this. So you can see that on the leftmost side, you have the uncertainties that might be related to just the hazard itself, might be related to the infrastructure as well. Then we have what we named our beautiful and powerful tool, those high fidelity models that we can simulate either the hazard alone or the hazard and the infrastructure together. And at the back end on the rightmost side, we can get the estimation of the hazard or the impact that we're going to see based on the hazard or the response of a structure and infrastructure that we might be looking at. So again, the middle thing is where we live and die for because of how computationally expensive it can be. Again, it's not across all the applications, but the more fidelity, the more detail you're giving to your model, the more factors you're integrating in, the more challenging it will become for that model to run in a reasonable amount of time. So, and in the probabilistic assessment, when you need to examine multiple scenarios, so you can give an educated guess that's not related only to a single event, but maybe to a range of events, you have multiple runs that pretty much you have to execute and go through that expensive routine multiple times. So this creates some huge time constraints when it comes to you providing some insightful information for decisions to be made. And in some cases, you don't even have the resources to go back and do that faithfully for all the necessary runs that you might have. So the big question that I will try to address is how can we integrate these computationally, but yet faithful in their representation tools in uncertainty codification settings where we have an increased computational burden. So is there a way that we can decrease that thing? And the short answer is that yes, we are fortunate enough to live in an era that artificial intelligence and machine learning are things that we are feeling comfortable around. So what we can do is we can characterize pretty much what we had as uncertainty in a certain way on the left, now called as an input, take that through a mathematical approximation instead of just a high fidelity model and get the output of interest that for us might be what we discussed as our structural response or as our estimation for the magnitude of the natural hazard that we're looking at. So this is the broader picture. Let's now narrow it down to the application that I'm going to discuss, which is related to the storm surge estimation. So how can we apply those ML tools in a setting, and what might be the peculiarities that we're going to stumble upon when we want to use those tools in storm surge and estimating storm surge. So I'll walk you briefly through the formulation of the problem because I kind of feel that this is important for each one of you to view their own problem into the specific setting. So in hurricane estimation and in prediction, we have two primary tools that are considered the main ways that we can estimate hurricane impact. And those are those two models. So these would be for us the high fidelity models. So we have some high fidelity models that are being extensively used by NOAA or by FEMA, by the US Army Corps of Engineers, where they can run faithfully hurricane scenarios and they can map on the output what would be the impact that those hurricanes will have. But guess what? They are extremely expensive. And if you focus towards it, which is a hydrodynamic model, it has a coupling of a variety of different models embedded into it. So the computational burden that I discussed, it grows exponentially and it reaches thousands of CPU hours. So just to run a single hurricane scenario, it might take a week in a supercomputer to be able to get the full picture of the hurricane impact from the moment it's being generated until the moment it sets landfall on a specific location. So, okay, we have our expensive simulator. Now we need to start thinking back on that picture of how can we formulate the input and the output that we want to see in the building of that mathematical approximation. So for the input in this specific case, we're interested, of course, what's the cause of all of that, which is the hurricane and it's in the hurricane track. So in that case, we want to characterize that input with some information that's related to track intensity and size of each event. So we want to be able to uniquely identify what would be those parameters that will make our input uniquely mapped to the output. So for the output, depending on what would be of interest, and in this case was the surge, you can be looking at the time evolution of the surge right here at the center of at the bottom of the center of your screen, or you can be looking just at the maximum storm surge itself, depending on what would be the quantity of interest. Bear in mind that these models are very robust, so they don't just give you information about the storm surge, they can give you information about the wind profiles, the sustained winds, and a bunch of different other parameters that are related to the impact that a hurricane might have in a location. But in that specific case, we're primarily interested in the output. So some things that you need to make sure once you start thinking about your problem in such a way of input and output, you need to make sure that everything is captured on the right way. So you have features that distinguish the different storms. Like we said, you need to make sure that your storm description is descriptive enough for the storm to be uniquely identified. You need at the same time to make sure that you're not over parameterizing something. So when you try to describe something, you're not digging in too much into details, but you may remain as simple as possible. And we'll see that down the road is also something that's very important when we build those data-driven methods. And you also need to make sure that you can express that temporal variability for the entire track history if necessary. So we have a phenomenon that moves a long time. You need to make sure that you need to describe this sufficiently enough to have the same response on a similar setup that you will be called to shoot predictions out. So for us in working with synthetic storms, we have a very well-defined input that's being comprised of the elements that you see over here. So you have the landfall location, you have the heading, you have the central pressure and the forward speed, and the radius of maximum weight. So these are the only parameters that you need for a synthetic storm to describe each storm uniquely. That's perfect. You have only 6 of them, which makes it not quite of a big of a challenge. But on the output, we have if we focus on the maximum surge, we have a single output, but for many locations across the domain of interest. So we are starting shaping what would be the input and the output of our model. And we have different dimensions of that model that I will briefly touch next. But let's see, okay, now we're starting seeing this in a form, in an aspect that says we have data. What's the goal out of that data? So the goal is to use that input and output, develop that mathematical approximation for the data-driven process in order to be able to do what? In a setting where you get a new input, where the output is unknown, you have trained that process to be able, based on the things that has seen already, to give you some information about what would be the potential output. So you're using it in a predictive way in order to be able, for an unknown scenario, to provide some educated guess of what would be the outcome that we've never seen before. So there are 2 ways that you can leverage that. You can leverage it to create regional flood studies, for example, and regional maps for that long-term risk assessment that I discussed, or you can even use that to do rapid risk assessments when it comes to real-time approaching scenarios where you will use that model to get a reliable prediction of how the evacuation should occur in certain regions, just to make sure that everybody will make it safely out of that area. Okay, so I have discussed the input, I have discussed the output. What remains is to shed some light on what's in between, which is what I was calling so far data-driven process. So in that case, we used for that data-driven process what we call kriging. So kriging is pretty much a Gaussian process with a linear underlying regression trend. Kriging has been used extensively for a bunch of different applications, and in many cases, they are geospatial applications where you have what? So just to give you a one-dimensional taste of what kriging looks like, so you have the exact function. The exact function is if I was able to run for all these x's exactly that high-fidelity model and get all the responses back from that high-fidelity expensive model. But we said that this is almost impossible. So what I end up with is what we call simulation experiments. So I have certain allotted time to run those simulations, and I'm allowed in this case to run just 5x, and I get the response for those 5x. So for me, the exact function is unknown. Being alone with those points, it's very depressing because you have no idea how the actual function looks like. But what you can do is, based on those responses, you can build what we call a predictive mean. So in that case, based on the information that's available, condition on the information that's available for you, you can go and develop the predictive mean. And actually, kriging can also give you the predictive variance of those of that predictive mean. So you end up pretty much with a response that behaves as a random process in the Gaussian space. So, and that predictive mean can be overlaid with your that predictive variance can be overlaid with your predictive mean. So instead of just giving a single guess, you can also give a window of uncertainty for that guess that you are providing based on the data that you have. So why kriging? So in this case, for the problem at hand, so why did we choose that data-driven or machine learning, you name it? Process is related to how the predictions are efficiently provided along with the uncertainty that I just said. It also enables for a multi-output, a parallel Gaussian implementation, so you can look at multiple locations, as we will see later on, at the same time. The database, so those initial points that actually anchored my predictive mean are very, very important. And just to give you an idea, the dimensionality that I mentioned earlier with respect to input is related to the training points, so the points that I need in order to be able to map that function. So in the case that n is quite small, then I will have a smaller, hopefully, database. So kriging is doing well with databases that are not of very large size. The size grows exponentially large. There will be issues related to inverting some matrices and all of that. So we have a very limited amount of scenarios, storm scenarios that we're looking at, and that's why that tool is kind of the weapon of choice in this specific case. So I will dig a little bit on one only project that's related to storm hazard analysis, and I will give you the challenges that we had. So we will be looking at a database that was given to us by the US Army Corps of Engineers that was related to an area in the North Atlantic coast line where we had pretty much 600 storms. So they were able to run through that expensive AdCirc simulator almost 600 landfalling storms. And here are these on the left side plotted all together. And we have the input that I described. So we have 5 parameters in this case, and we have as output more than 500,000 points. So we want to be very detailed on the way we are recording what's the impact of that hurricane. We're not interested in just a single point. We're interested in a multi-output prediction. So that brings to the table quite of a challenge. Why? Because you have to address that high output dimensionality somehow. So we have, like I said, more than 500,000 points. Can we work with 500,000 points at the same time? Thankfully for us, because we have a problem that's spatially related, we can go and downgrade that. And in order to do that, we can use other tools that are related to computational statistics, and those are dimensionality reduction techniques. So in all reality, you can have 2 paths down on this. You can use one data-driven model, one surrogate model for all the predictions, or you can use multiple ones by leveraging that spatial correlation that's there for you in a linear mapping that PCA is offering. So we're going to opt for the second one because it offers higher accuracy. The first one, it's still doable, but it will have some accuracy flaws in it, primarily because you're trying to map an entirely different region of 500,000 points into the same model. So the model reaches some capacity that it cannot exceed when it comes to how reliable it is on its predictions. But if you try to condense information in different ways, that will help the model to gain higher accuracy to that extent. So the challenge that we were given was the following. They wanted for each of these locations to have pretty much what we call a hazard curve. So they wanted to have for each location a way to quantify the probability of exceeding certain surge levels for different thresholds of the quantity of interest. So we had the high dimensionality, and then we had a bunch of information that we had to condense on that dimensionality. So the main idea in this was the following. It was, we have a very large region. We want to condense the information in an educative way. So maybe we should condense, we should cluster together, we should group together the information so we can work efficiently with less amount of locations. So that was the first idea. Then we discussed, okay, how can this be done? Do we have an informed way that we can group locations together so we can get those hazard curves in a more efficient way? The answer is that yes, you can do that, and we'll see how after this slide. So the way we did it was pretty much clustering points together, then getting the cluster centroids as a representative for those certain regions, and developing for those cluster points those curves that we needed, the hazard curves, and then interpolate those curves in the whole domain. So what we leveraged here extensively was the fact that there was special correlation that we could map in that specific instance through different methods. One was the geospatial interpolation, the other was the clustering, to make sure that we can work with a much smaller number of points. That was for us to be able to develop something that would be running efficiently, fast, and accurate at the same time. So we wanted to balance that accuracy and let's say timely manner of getting predictions up and running. So I'm going to show you the application that we did on that, on the database that we discussed already. And we have, in every problem, there are more challenges as you dive more into the problem. One of the other challenges that we encountered was the fact that the domain of interest, it's not always stressed under the same way under different storm scenarios. What that means is that there are locations that they will get inundated in certain scenarios, and there are certain locations that won't get inundated in other scenarios. As you may imagine, if you have your house somewhere, you have a hurricane approaching, if it's close to you, you'll see storm surge coming your way. If it makes landfall, I don't know, hundreds of miles away from you, you might be still in the region that's getting affected, but you will see none to maybe a few, I don't know, inches of water tops. So that creates some discrepancies that we had to take care also in order to be able to create those hazard curves efficiently. And these are some of the results that we had for different locations that had also that additional challenge of not being inundated the whole time across the database. So in this case, you can see that we have different variants that we examine. I won't dig into details on how those variants were created, but the reference, which is the yellow one, you can see that in most cases, we are able to capture exactly with all those variants, the behavior that we would like to see for the hazard. If you don't like hazard curves and you are more into hazard maps, so here are pretty much you looking at the entire domain of interest, simply fixing the threshold that you would like to see, the return period that you would like to see, so 1 in 500. And these are the two different variants. The reference is always on your left, the outmost left one. And you can see that even on a contour setting, you get a very, very good accuracy, with the accuracy getting a little bit more challenged when it comes to nearshore nodes. Why is that? To nearshore locations? Because again, you have that leak of information across the different scenarios. So not all the scenarios will inundate the same regions, which means you have that discrepancy that you need to cover across. And just to go into my conclusions and briefly fly in some projects that I was also involved based on the work that I did. It was one that was related to FEMA and how they could update their zone, the flood zone regions that they have. So in that case, the challenge was coming from a different setting. They wanted to make sure that based on a very fixed number of the simulations, so the high fidelity simulations, the data points that we had were much less than what they needed. And we had to develop based on those points surrogate model to be able to add more to that database so we can make it accurate enough. So this is the entire database they had. We had to split it, so we had to hide some of this, and we had to train on the rest our model just to make sure that we can predict the hidden one with accuracy. That's very common when you have data that's already given to you and you cannot produce more. There's only one way that you can validate. You need to hide some from the model and then ask for the model to predict for those and then compare to what the output is that you already are aware of. So in that case, we had the entire database. This is how the hazard map would look for that case. Here we had just 1/3 of the simulations, just with a crude Monte Carlo. And in that case, we had 1/3 of the simulations faithfully run into an expensive model. And the rest, the 2/3 were added with a surrogate model. So that you can see that pretty much if you compare, and I can also give you the error maps, you can see that pretty much the error fluctuates along 0. So what these maps are giving you, they're giving you the difference between the Monte Carlo approximation and the approximation that uses the Monte Carlo and the surrogate model. And you can see that you have an error that pretty much fluctuates around 0. So we demonstrate to them that it's better to kind of compensate for the fact that you cannot do more expensive runs with developing a data-driven model based on the runs that you already have and use that model to pretty much complement your database and augment your database in an educated way. So just to conclude here, there are machine learning tools out there and they are growing extensively in the applications that we see. And they can be tailored to engineering problems. You need to be aware that each problem will have its own challenges. So just grabbing an off-the-shelf method and try to apply this to the problem that you have, 99% of the times won't work, simply because there are inherent challenges to each problem that need to be taken into account. You need to be aware of both words, not just the word that looks at the data, but also the word that looks at engineering and how those quantities are impacting our lives. So you cannot just be crudely assuming that an algorithm, because it works without any error, gives you the right results. There are ways that we can tackle computational intensive processes by relying on those models and completing pretty much the picture when we're lacking information by using those models. You can even have sea level rise, and we have attempted to do that, and it's successful, incorporated in your predictions. And yes, in that sense, you can also provide future insights of the generation of databases that are related to climate change and climate and sea level rise scenarios. And with that, I hope I didn't run a lot out of time. I would like to thank you for your attention, and I will gladly take any questions that you have.
Thank you, Dr. Kyprioti. Any questions from NHERI GSC?
I have to say that with 30 minutes at hand, I couldn't dig into many details, but for the sake of the audience, I'm assuming it's better to discuss rather than me ranting about math.
Yes, I see your hand up. Go ahead and ask your question.
Hi. I have a question regarding the return period of the storms. So do you have how do you quantify the return period of synthetic storms?
Yes, so this comes with the database description. So what they do, the database that we were working with has already embedded, so that the way the population of the storm is selected is related to return periods and historical data. So the way that 595 storms were created, it embeds in the process of selecting the characteristics of each storm with that probability of exceeding a certain event. So there is it was not our group that did that. There was the Army Corps that gave us the database. So they had already pre-selected what would be the return period for each of the storms that we were dealing with.
Okay, thank you.
Sure.
Yes, question.
Hi. So when you're calculating the probabilities of exceeding a certain value, did you take that prediction variance coming out from rigging, or
No. I'm working with the means, but I have colleagues of mine that worked with the variability as well. Yes, you can totally do that.
Okay, thank you.
Yeah.
Any more questions? Oh, I see a question. Okay.
Hi, I don't know a lot about modeling, so maybe, like bear with me in this question, but I was wondering if you can talk a little bit more about how you incorporate rapid assessment measurements into these models and what are some of the challenges. I imagine that this is done via remote sensing tools and things like that, and I don't know how expensive that is, how reliable, whether you use like satellite images, what are the trade-offs in using that data for your model, given that I don't know if you need some sort of cleaning that takes a lot of time or not, or like, those sort of things. Thank you.
Good question. Thank you. No, it's not a bad question. So let me clarify something. In a real-time setting, the way you would be using this is after an advisory is issued. So the way, for example, hurricanes work, right? You get advisories as the phenomenon progresses, and yes, those are coming from the National Hurricane Center or from NOAA, National Weather Services. They kind of come all together. They do monitor the event. So they do fly planes that are going almost next to the eye. They do a bunch of calculations. But at the time you get the advisory at your hands, that uncertainty has been wiped off. So they give you some certain numbers that they say, okay, at the time that we saw it, the last 6 hours, it has these characteristics. So based on those characteristics, there are two ways that you can use them. Based on those characteristics, you can just predict one single output that says, okay, for the region that you're saying that's going to be heading, that's the outcome. But what you can also do is that now that you have that very expedited tool that can do a bunch of runs in no time, because it relies only on math. There is no hit and run button, right? You can investigate different scenarios. So instead of just getting the single prediction that they're trying to give you through the advisory, they give you also a cone of uncertainty. It says, okay, there are a bunch of different scenarios that can evolve based on that single more dominant, let's say, track that we think is going to follow. So what you can do is you can investigate all of them in the amount of time that you have. So do you have like 3 hours in your disposal? Do you have 6 until the next advisory? So you can investigate a bunch of different scenarios and tell them, hey, based on what the National Weather Center is giving me, I have investigated 300, 600. And there are other projects that I was involved in that we tried this and it works. So you can give them a much, deeply investigated case scenario rather than just one. Because also NOAA and everybody else is trying to do some estimation. So you see that when they give you the advisory, they also give you the affected area, right? So they say, okay, these are the levels of surge that we're looking at, but they don't have, because they are relying on models that they are quite expensive, based on the time window that they have, they can only run, a couple of hundreds. By having the data-driven model, again, not to replace, but just to complement what they're doing, you can explore a much wider range of potential events that can happen and give them a more reliable prediction. When it comes to data, because you brought another interesting point up. When it comes to data that you're measuring, and there is inherent error, or there is an inherent noise in those data, that's a separate line of data-driven models that you should follow. Why? Because on the numerical models themselves, we assume that every time we will give, so there is what we call one-to-one mapping. So every time I'm going to give you an X and it will go through that function, I'll see the same Y. The moment the Y starts fluctuating under the same X, you're looking at a more complex problem, because there is some uncertainty that's embedded into the process this itself that it throws you off in your prediction. So there you need a tool that will be able to capture that fluctuation. There are ways that you can do that, even with data that's being recorded in real time. You just, yes, you need to be aware of the level of noise that you have. You need to make a bunch of comparisons between the inherent level of noise in your data and how much noise maybe your model or error is adding to the specific prediction. So yes, there are ways. It just you have to be a little bit more careful because there is not that one mapping.
Thanks so much.
Sure.
Anamika, did you have a question?
Yes, thank you, Dr. Itikari, for the wonderful presentation. I wanted to know more about your choice of surrogate models. Like when you said it isn't one size fit all. So when you're choosing the physics, especially when it says stochastic and Gaussian, and then you choose, are there other models that you're trying and then you land on this? And what is the selection process and how do you actually come up with a model that fits with you, with the one hazard that you're working on? Because we work with different hazards. So what should be looking into it when we're trying to find out surrogate models that we could put into our research?
Good question. So that's actually a very fundamental one. So there is something that's called model parsimony. So you're always looking for a model that will give you the best performance, that's simple enough and you can control. So that means that, yes, I know neural networks are fancy and everyone wants to work with them and say that they're being, like using neural networks to predict something. But this is where you are diving into some computer science things that say we don't know what exactly is happening, but it's working. So there is a lot of, I don't know, hand waving, if you've ever followed the, like neural network class. So the short thing is you look at your problem. You look at the data size that you are trying to handle. Then you look also at what's the goal? What do you want? Do you want just a prediction? Do you want to have the uncertainty window as well? Again, there are ways that you can get the uncertainty window from other processes. It just requires more computational effort. Some cases, like here, it comes almost for free because it's part of the estimation that you're doing. So you look at your data size, you look at the nature of predictions you want to do, look at the nature of the problem that you have. Like I mentioned to Lydia, yes, you have to be aware whether there is noise, what's the level of noise, but are you allowed to denoise, up to what extent? Because then you're tainting the data. So there is a bunch of questions you should ask first on your data set or the problem that you're trying to solve. Then you're starting simple. Always start simple, because you might have linear regression beating everyone else. So it doesn't mean necessarily that you have to go with the most extreme way to do that. So then you are asking, what's the relationship that I'm trying to map between the input and the output? Is it highly nonlinear? Could it have a linear component that's very strong that maybe it's good enough? So you need to start diving a little bit into how the nature of that problem, the physics works before selecting the tool itself. And always try to keep it simple. The thing that we are struggling with is I don't want something to get results to run for a week when someone next to me can do it within an hour. So I want to beat the 1 hour person, right? So I want to be as much as I can efficient and accurate at the same time. So I would start always by simple things and then escalate to see what more you get if you escalate. Because that's the other thing. It's like, is the difference that you get in your accuracy justifiable by the fact that you need to run in a supercomputer in Texas and back to just make it work? Whether, you could just run in your PC and get something that would give you, I don't know, half an inch of water difference. Trust me, when it comes to coastal flooding, half an inch won't change anyone's lives, but half a foot, it will.
I mean, also a little more question, but so what if I know my process is very uncertain and comes with a lot of uncertainty, especially if it comes with turbulence? Do you think we could are we anywhere near using surrogate models, or it's very far off in the future?
I think So I'm going to talk to you now like a computer science person. Do you have data? If you have data, we can do anything. The problem where the problem is getting pushed right now is like how much data do we have to train something? If we have enough data, we can train whatever you want. No matter how non-linear it is, no matter how complex it is. The problem is though that, again, like any other tool, and that should be stressed along the way, it's a predictive tool, right? So it tries to make predictions. Same as every other tool, when you're asking it for something, even if I ask a person, right, that lives in a certain area, what's the weather going to be in 3 weeks from now? I'm extrapolating on your knowledge, right? Which again will hurt how good of a prediction you can give me. So all those tools are comfortable within the things that they know. Once you try to stress them out on the things that they never seen, they can fail horribly. So you need to be aware that what you're trying to make predictions for is within the domain that the model has been trained on. So if you want to do extreme events, you need to have extreme events in your numerical model first, and then try to train something in between, right? Yes, you can extrapolate in some cases a little bit, but this is a very, very delicate conversation that I would like to ring the bell and say, don't do it a lot. Or if you do it, try to see the way you're extrapolating, what does exactly do.
Okay. Thank you.
Sure. We have another hand. Heider?
I think that's our last question. Hader?
Yes, hello, thank you. Thanks for a nice presentation and very good topics. And just I'm not catch on the from starting the presentation, but at the end, I have some question about there is a variability for connecting with the Google Earth Engine, for example, and integrated with other indices about searches and about, for example, hurricane or because Google Earth Engine it's a very vital tools for for connecting coding and connecting the integrating the database. And the other issue can integrated with, for example, for Earth resilience. Why you made for example, everyone when you made research about risk assessment also need for vulnerability and resilience and to see the impacted area and what's the developed area against this against each hazard. For example, can integrated the wind speed with the canopy high or other searches or hurricane or other flood and can integrate it within Google Earth Engine or other model. Thank you very much.
Sure, absolutely. Okay, so I see two legs in your question. The first one says, can you integrate information about infrastructure, right?
Yeah, infrastructure and natural hazard, yes.
Yes, another natural hazard. So this is giving you the first information so you can compare the infrastructure to the hazard that's been facing, right? So that's what the hazard map is doing to some extent. Can you overlay different events? I would say you need to overlay them from before, because here's the thing. If it's a entirely different event and it has an additive effect, you can, absolutely. So you can have two different surrogate models giving you predictions, giving you hazard maps. If they are somehow connected, so if we're discussing compound flooding, for example, so if there is some interconnection between the one hazard and the other, you need models, you need data points that will capture that interconnection, simply because just adding one on top of the other, it's not how the phenomenon works, right? And we're discussing physical phenomena. So in order for something to be multi-hazard, it could, if it has an additive effect. If you're discussing something that will have an integrated effect, you need to be able to capture that integration, to predict for that integration. But pretty much by having the hazard map, you can tell whether certain structures and overlaying that with your infrastructure inventory, You can tell how many structures will be under trouble and what level of trouble. And you can quantify that, the vulnerability, any way you want. Do you want to do it in dollars? You want to do it in damages? It's up to you. It can be overlaid, yes, with wind. So you can predict wind profile and then create a framework that will compare to locations and infrastructure and the height of canopy or whatsoever, and make some decision making, kind of framework after that. The other one that you said that it's interesting is about the GIS. So having the information overlaid in geospatial environments like Google Earth or any other GIS kind of environment that you want. That's also doable because you have the information already overlaid in a geospatial environment. So you have lat and long for everything. So definitely can be integrated into software that are dealing with inventories on a geospatial description. Does that answer your question?
Thank you very much.
Sure, absolutely.
Well, thank you, Dr. Kyprioti, for a wonderful presentation and a great conversation.
Well, there is a question. Wait, I think, Richard, there is a question in the chat. Am I right?
Sure.
I think I noticed the difference is that. Can you check? I'm seeing one question for sure. Can you check about whether?
Oh, I see. Yes.
I see Rajendra's question. I don't know if he's around, but so it was like I noticed the difference in stress concentration in the comparative result you presented between Monte Carlo and the surrogate models, which you kind of provide a brief explanation of why this happened. When you mean concentration is here around, I guess. No?
Yes, he's here.
Okay. Just quick question, just quick clarification, I would say. When you mean concentration, do you mean the error? Do you mean the fact that there was error in certain regions when I compared the Monte Carlo one?
I see in your model you presented there were the different color in surrogate and Monte Carlo, right?
Do you mean here where I'm comparing it to the reference, to the baseline? Right?
Yeah. Yes, of course, yeah.
So you can see what that pretty much tells you is that if you just have 1/3 of the simulations and you do just a Monte Carlo analysis, you're missing a bunch of regions because you're working with a smaller data. So 1/3 was how much FEMA could do, and based on the resources, that's how much analysis they could do in a faithful, in a high fidelity software, right? If you had just that, that's how close you can be to the reference case, which was this, right? So they wanted just 1/3 of the computational cost. That's what they could afford. And they said, is it okay if we stop at that 1/3? Again, bear in mind, we had the whole database, but they said you need to carry that 1/3 because that's how much we want to spend on our future investigations. We don't want to spend more than 1/3, right? So we told them, okay, if you had just 1/3 and you were doing the Monte Carlo analysis, that would be the error to your reference. If you were doing the Monte Carlo with 1/3, so if you were giving us that 1/3 and we were training a model on that 1/3, we could predict the other 2/3 based on our data-driven model and give you this error with respect to the reference. So why the concentration here? Like I said, the challenge always is to nodes that are close to the coastline or even inland. Why? Because those nodes under the 300 scenarios that you might have won't always get inundated. Because depending on the geomorphology, if a hurricane is not as strong as the previous one, it might not reach a certain location inland, while a stronger one might reach that and even surpass that location. So the challenge arises from the fact that you have incomplete information across the different storms. It's like you having a house in the inland area here, like Galveston, no, sorry, Galveston. What's the bay here? I don't remember now. Liking this is North Atlantic. It's anyway, the bay that's here after New York City. It's close to New Jersey. I don't remember the name. Forget it. I won't remember now. It's off my mind. So if you have a house that's further inland, and you don't know if every single event will reach your house, right? While if you have a house that's right by the sea, right at the coastline, chances are that every single event that will happen in the neighborhood will hit your house. So you have incomplete information because you've seen water coming in your house only for a few scenarios, not for all of them. While the person that has a house in the front line of that coastline, every time a hurricane comes, they will record some level of water. So they can tell you in between, so if they've recorded, I don't know, 100 times, they can tell you in between those 100 times what will be the 101st. While if in your location you have recorded out of 100 times only 10, it's hard to tell what's going to happen next, right?
Okay, thank you so much. Okay, I got.
Sure, yes,
Sure,
absolutely.
sure. Yeah.
Great. Again, thank you, Dr. Kyprioti, and thanks everyone for being here. It was very educational.